In this lab, we will continue with the time series analysis of the COVID cases um, for confirmed data, um, death data, and the recovered data. We were looking at step 4 in the previous lab. We will continue with step 4. Perform ARIMA, autoregressive integrated moving average prediction on the confirmed New Zealand data to predict the number of cases in New Zealand. Let's so we used autoregressive integrated moving average function in stats models.tsa.arima.model to make ARIMA 111 model, and we also used it to make many more models in the range of P in the range P, Q, and D in the range 0 to 3. So we looked at all the combinations from 0 to 3 of P, Q, D, and we formed the model. And we also plotted the graphs, and we and we saw that the models, the highest prediction was 2.25 exponent 6 from the different ARIMA models. And now we will we also used the library from statsmodels.tsa.statTools and the library is EdFuller to find the EdFuller statistics and the p-value. We found that the p-value was larger than 0.05, which failed to indicate that the time series is stationary. So the time series is non-stationary. Now we look at the differencing in time series. Differencing is a technique to make a time series stationary. It is the transformation of a time series into the difference between consecutive data points. Differencing is performed by subtracting each data point from its predecessor. For example, the phase difference of a time series yt is equal to yt minus yt minus 1. Differencing can help to remove the underlying trend and or seasonality in the data, thus making it stationary. You might have to apply differencing more than once to obtain a stationary series. The autoregressive integrated moving average model with parameters P, D, Q includes P, which is autoregressive order, Q, which is differencing order, and P is autoregressive order, D is differencing order, and Q is moving average order. The D term in an autoregressive integrated moving average or seasonal autoregressive integrated moving average model indicates the order of differencing applied to make the series stationary. An autoregressive integrated moving average of 1, 1, which is the autoregressive order, differencing order, and moving average order equal to 1 model, for example, indicates that the series has been differenced once. When you say D equal 1 in 1, 1, 1, it means you are differencing the series once. However, this may not be enough to make the series stationary, thus the warning. When you set D equal 2 in 1, 2, 1, you are differencing the series twice. This may make the series stationary if it initially had a trend and a seasonality, which is why you are not getting a warning in this case. So let's find the value of D, which is good for our autoregressive integrated moving average model. That is no warning. Could we code the model again? So let's code the model again. From stats models, .tsa.arima.model, we import arima. Then we fit the arima model. Let model equal arima of confirmed New Zealand name, comma, order equal 1 to 1. Let model fit equal to model.fit, open and close bracket. Let's make the predictions. Let's print the predictions as well. So predictions equal model fit dot forecast steps equal 10. We will, instead of printing the predictions, let's plot the predictions. So we have to have plt.plot. And we can see the predictions, it is linearly increasing. And if we have 1 1 1, let's see what happens. It is for 1 1 1, it is also, the predictions are also linearly increasing, positively increasing. Now we may ask, how can we optimize the values of PDQ to make sure that we have the best parameters for our model? And also, how do we evaluate our model fit? This brings us to the concept of the AIC value. The Akaike Information Criterion is a measure used to evaluate the quality of a statistical model. In the context of time series forecasting and autoregressive integrated moving average models, a lower Akaike Information Criterion value generally indicates a better fitting model. Given the data, the Akaike Information Criterion takes into account both the complexity of the model and its ability to fit the data. The formula for Akaike Information Criterion is equal to 2k minus 2 ln bracket L, where k is the number of parameters in the model and L is the maximum likelihood estimate of the model. What does AIC do? Akaike Information Criterion penalizes complexity. Akaike Information Criterion adds a penalty that increases with the number of parameters in the model. This discourages overfitting, which is crucial when selecting among multiple models. More complex models are penalized more heavily. Rewards goodness of fit. Akaike Information Criterion also rewards models for how well they fit the data. Models that fit the data better will result in a higher likelihood, which leads to a lower AIC value. So higher likelihood will lead to a lower AIC value. So 2k minus 2 ln L. So we are subtracting the 2 ln L, and higher L will give us ln of a higher ln of L value, and we will be deducting higher value from 2k. And if the number of parameters increases, which is the k, then 2k increases, and so this discourages overfitting, which is crucial when selecting among multiple models. More complex models are penalized more heavily. How is it used? In practice, you would usually compute the Akaike Information Criterion values for multiple models and choose the one with the lowest Akaike Information Criterion value, provided that the difference is significant. Some statisticians suggest a minimum difference of 2. How to perform grid search to obtain the best values of PDQ for our autoregressive integrated moving average model. The stats models library itself does not offer an out-of-the-box automated parameter selection feature for autoregressive integrated moving average models. However, we can manually implement a grid search to identify the best autoregressive integrated moving average parameters based on some criterion like AIC. Write one or several loops to test all the combinations of PDQ from 1 to 3. Example 1 to 1, 1 to 2, 1 to 3. Let predictions equal pandas.data frame open and close bracket, that is to initialize empty data frame. For P in range 1 to 4 and for Q in range 1 to 4, for D in range 1 to 4, let name equal F apostrophe sign curved bracket. Inside the curly braces we'll have P comma and then inside the curly braces we'll have Q and then close the curly braces, comma. Inside the pair of curly braces we'll have D, close the curved bracket and close the apostrophe. Fitting autoregressive integrated model, let model equal ARIMA of confirmed New Zealand num, comma, ODA equal PQD. Let model fit equal model.fit open and close bracket. Making predictions, let predictions, the column is the name. So the column name is the name that we found, equal model fit dot forecast bracket steps equal 10. So this will forecast 10 values. And printing predictions, we get the, so the column name is the PQD values, and the row, the indexes of the data frame is the date, and those are the 10 dates, and that's including 10 March 2023 to 19 March 2023, and there are 10 predictions that is done. Now we will plot predictions. plt.plot of predictions. Use the numeric index for x-axis, plt.show open and close bracket. Let's see what that does. And we also want to rotate the x-axis ticks for readability, plt.x ticks rotation equal 45. We have to run this again. And predictions.index9 will be the 9th index from the predictions data frame, and that was 19 March 2023. Now when that has done, then we will come back to that. Now let's define the PQ and PD and Q parameters to take any value from 0 and 4, between 0 and 4. Let P equal D equal Q equal range from 0 to 4. Print P comma backslash n backslash n, so which means that we are leaving two new lines, comma D comma backslash n comma Q. So P, D, Q are in range 0 to 4. Let's import itertools. Import itertools library. Generate all different combinations of PD and Q triplets. Let PDQ equal list of itertools dot product of P, T, D, Q. Printing PDQ, this will print all the combinations of values from 0 to 4. And as we can see, it prints all the values. Now, let's see if that is done. Yes, that is done. So let's run it. So we get here, so we can see that the x-tick values, they are rotated 45 degrees. Now let's label these graphs. Let's label the graph by using PLT text. For I in range 0 to predictions.shape1, so predictions.shape1, let's see. Predictions shape is 10, 27. So predictions.shape1 will be 27. So for I in range 0 to 27, plt.text of predictions.index9. So .index9 is the last date, which is 19 March 2023. So x equal 19 March 2003, which is over here, and y equal predictions.index location 9 and the value from ith column. So predictions.index location 9 will give us all these values in the ninth row, ninth index row, and then we take the ith column. So that's what we're doing over here. So so y equal predictions.index location 9 and ith column, and the value is predictions.columns I. So predictions dot columns, so the column names are these, and the column name will be, ith column name will be chosen. So let's run this. So we can see that the top one looks like for 3, 2, 2, and that gives the highest predicted value on 19th of March 2023, and the lowest is for 3, 3, 3. Okay, so we come back to this one. So import statsmodels.api has SM, import itertools, import awnings. Now there will be awnings printed, so we don't want the awning signs to be printed, so we import awnings, and awnings.filter awnings of ignore, category equal user awning. Awnings.filter awnings, bracket ignore, category equal runtime awning. Define the PD and Q parameters to take any value between 0 and 4. Let P equal D equal Q equal range from 0 to 4. Generate all different combinations of PD and Q triplets. Let PD Q equal list of itertools.product of PDQ. So it will give us all the combinations of in the range 0 to 4, and these will be the values. Then run a grid search with PDQ and seasonal PDQ parameters calculated above and get the best AIC value. Let best AIC equal np.infinity. So best AIC equal infinity. Best PDQ, let it equal to none. Let best model equal to none. For prom in PDQ, so we are running the loop for each of the values in PDQ. Try colon model, let model equal arima of confirmed New Zealand num, order equal prom. Let model fit equal model.fit open and close bracket. Get the AIC value. Let AIC equal model fit dot AIC. If the current run of AIC is better than the best one so far, overwrite it. If AIC is less than best AIC, so to start with, the best AIC value was infinity. So if AIC is less than best AIC, then best AIC equal AIC, best PDQ equal prom. So to start with, it was none, and now best PDQ will be prum, best model will be model fit. Accept, try, accept, continue. So if AIC is not less than best AIC, then we continue with the other values in PDQ. Print, bracket, F, apostrophe sign, best ARIMA model is calibraces best PDQ with AIC equal calibraces best AIC. Print best model dot summary open and close bracket. And so best ARIMA model is 3, 2, 2 with AIC equal 21,990.6255 and so on. And the summary looks like this.